DC biasing of bipolar transistors part 3. Self-bias or emitter bias. Bias stability is an important thing when you're designing a transistor circuit. Let's look at our fixed bias circuit and let's discuss some of the weaknesses with this biasing arrangement. First of all, I've chosen these values. I haven't given the actual values of RB and RC on this diagram, but they've been chosen to provide these currents in the base and the collector. And the beta for this particular transistor has been chosen to be 35. Here's the characteristic curve for this transistor, and I've shown on the diagram here, I've marked on the diagram here just one of the characteristic curves for the base current of 0.2 milliamps. The Q point here is the point which we have biased our transistor, and that would, if I was to read off the values of VCE on this curve, and if I was to read across the value of IC on this curve, I'd find that IC was 7 milliamps, and that VCE would in fact be the voltage VC at the voltage at the collector at this with this arrangement. Let's now consider what might happen if we were to replace this transistor with a new transistor having a slightly larger beta value. Now this might seem strange, but in fact manufacturing transistors is not that easy, and for a given process you can get a range of values of beta for the same transistor produced by the same manufacturer. So let's imagine that we've replaced this transistor with one having a beta of say 50, and we plug it into our circuit. Well, as you can see, because beta is 50, we've now got a larger collector current, and the effect this has on our stability curve, you'll see at the right hand side here, is to move the Q point to a closer towards the saturation point of the transistor on the left hand side. Now this means that the voltage at the collector will have dropped, and it might be okay. We might still be within our expected tolerances for these voltages, but there is a possibility that we could move the Q point so far away from its original point that we might actually enter the saturation region, or in fact go the other way into the cutoff region, and that will affect the behaviour of our circuit when we start to apply or use the transistor as an amplifier. So it's not a very satisfactory arrangement, and that's one of the reasons why fixed bias circuits are very unusual for small signal amplifiers. So let's show you a new way of biasing the circuit. So here's our old way, the fixed bias arrangement, but if we move from that to a self-biasing circuit, you'll see the following changes have to be made. Right, what we've actually done is we've introduced, instead of having a single resistor RB to provide the base current, we now use a potential divider circuit using resistors R1 and R2 to hold the base voltage at sufficiently high value to provide the correct base current, and on the other side of the transistor you see that in addition to the collector resistor we now have an emitter resistor. Now usually this arrangement, these arrows are meant to, the fact that I've used larger arrows going through R1 and R2 than is going into the base, is I've done that deliberately to indicate that the base current is usually a small fraction of the current that actually passes through from the supply through the resistors R1 and R2, and typically it's about 1/10 of the of that current. And that means that the any fluctuation in the base current will make only a very small difference to the actual voltage of the base voltage, and consequently we can assume, or I'm going to assume in this discussion, that the base voltage stays almost fixed, and therefore we can now look at the effect of what might happen if things change, if the collector current changes through the value of RC. So when the collector current IC passes through RC, a voltage is dropped across the load resistor, and that means that the voltage VC here is smaller than the supply voltage V, and the difference between these two voltages is in fact IC times RC. That's the difference between the two. So I could have actually written VC is equal to V minus IC times RC. So that's our current operating voltage for the collector. Now the other thing to note is that because the emitter is now no longer collected directly to ground, so therefore the emitter voltage isn't at zero like as it was in the fixed bias arrangement. It's now going to be at a voltage which is slightly bigger than zero, because a current IB plus IC passes through RE, and that gives rise to a potential drop across the resistor RE, and therefore holds the emitter resistor VE, the emitter, at a voltage VE which is greater than zero. Typically that's usually about 1 volt. So the now that means that that effect means that and also I should mention that the current flowing through the emitter resistor is not just equal to IC, but is actually equal to IC plus IB, because by Kirchhoff's law this transistor acts like a node in an electrical circuit, and as we know, the current entering that node must be equal to the current leaving it. So we've got IC and IB entering the transistor node, and we've got a current IB plus IC leaving it. Right, now we're going to see now that this resistor, the importance of this resistor is to act in such a way as to produce feedback to the circuit, and it's a negative form of feedback, holding, and that has the effect of keeping the transistor more stabilized and less susceptible to variations in the collector current. Now the collector current can increase for the reason which I've mentioned already, that we might replace this transistor with another one having a different value of beta, but it might also increase for other reasons. For example, when the transistor gets hot, the collector junction or the collector base junction can, as the temperature rises at the collector base junction, in fact the current carriers that are generated in the semiconductor material can cause the collector current to rise, and this rising in the collector current has the effect of raising the voltage at the emitter. As you can see, the collector current has increased, and that extra current passing through this resistor RE has caused the voltage here to go up. Now what has that done? Well, that's had the effect of reverse biasing. The voltage that was at the emitter has now increased. So consequently, because the base voltage is fixed and the emitter voltage has gone up, it means the base emitter voltage has actually gone down. So for example, it might have been originally at 0.65 volts. It might have now gone down to say 0.63 volts or even 0.62 volts, something like that. Now that's the effect that's had is to reduce the base current. As you can see, the base current has now been reduced. Now we know that the beta value for the transistor is the ratio of the collector current to the base current. So therefore, if the beta value has gone down, if the beta value is fixed and the collector current has gone down, that means that the base current has gone down. I've got my figures around the wrong way. The collector current must also go down. So consequently, the collector current gets pushed back towards its original value, and the base current then increases slightly back to towards its original value, and the transistor is pushed back to its the original or the same operating point on the characteristic curves. So you can see the way this circuit is working. It's working to create a self-biasing or emitter-biasing arrangement, and that makes this biasing arrangement much more popular for small signal transistor amplifier circuits than for the self-biasing arrangement that we looked at in the previous video. I hope this has helped a little bit, and on the next part 4 we'll look at some calculations on how we calculate the resistor values when we want to set up an emitter bias arrangement for our transistor circuit.